were actually discussing the time dependent Schrodinger equation, which is the basic equation this is the equation, and in fact this equation can describe all the phenomena that one is interested in chemistry. In fact, it forms the complete description of chemical phenomena, unless of course you are interested in relativistic effects, which normally chemists are not interested. Okay. Now, we wanted to solve this. In fact, we were thinking of a one dimensional example where we wrote this equation in this fashion. Well, in general, the potential will depend upon time also, and I told you in the morning that is what happens in spectroscopy. If you are doing spectroscopy experiments and if you allow electromagnetic radiation to interact with your molecule, the potential energy, I mean the Hamiltonian will contain terms that are dependent upon time, which will change with time. But if you are not thinking of such situations, then the Hamiltonian, this is the Hamiltonian operator, and it is independent of time, and in such a situation we were trying to find the special solutions. Why were they special? They were special because the time dependence and the position dependence could be written separately and then multiplied together to get the total function. And we made this assumption, put it back into this equation and arrived at two ordinary differential equations. Let me just write them also. The first one said that I h cross 1 by capital T of t dou capital T of t by dou t should be equal to a constant, and the other one said should be equal to the same constant. Now, let us look at this equation. This is an ordinary differential equation, and I may also point out that even though I have put partial derivative notation here, this is something that operates upon capital T. Capital T is a function of small t alone. So, there is no other variable that has to be kept constant in this partial differentiation, and therefore, it is not really necessary for me to use partial derivative notation, because capital T after all is a function only of small t. So, I will just replace it by d capital T by dt, which will be the usual notation for differentiation, right. And if we look at this equation, this is a simple differential equation which can be easily integrated. Remember, E is a constant, it does not depend upon position, it does not depend upon time. So, it is just a constant. So, what you would do is you would integrate this. In fact, you can write this as I h cross d ln capital T by dt is equal to E or I can take this I h cross to the other side and put it here, and this you can integrate after multiplying by dt. If you integrate it, you are going to get ln t of t is equal to E into t divided by I h cross plus a constant of integration. That is what happens. I mean, there is a simple differential equation. If you multiply by dt and integrate, this is what you are going to get, and taking exponentials of both the sides, you are going to get capital T of t to be equal to exponential of E t divided by I h cross plus C1. No, I am going to do two things here. One, you have e to the power of C1, C1 is a constant. So, e to the power of C1 itself is a constant. So, I will write this as e to the power of C1, which as I said is a constant, and then I will have e to the power of E t by I h cross, but 1 by I. You know that 1 may be written as minus 1 into minus 1, but minus 1 is actually I square. So, therefore, you can easily see that one I and another I may be cancelled. So, you will get minus I. So, 1 by I is easy to write it as minus I. So, I am going to use that, and therefore, this part will become e to the power of minus I e t by h cross. And as I said, e to the power of C1 is a constant. So, why I take the trouble, as I have been saying in the morning, I am lazy. So, I do not want to write unnecessary things. So, this is just a constant, maybe I can denote it as some capital A, which itself is a constant. So, what is it that I have done? I have solved and found what capital T should be. It has a very simple appearance. It is just a constant multiplied by e to the power of minus I e t by h cross, that is all, very simple function. And having solved that, we will look at the second other differential equation written here. If it is clear that if you multiply by 1 by psi of x throughout, I can remove this 1 by psi of x, or let me just remove it here, and I am going to put it here. And this is a simple ordinary differential equation. In addition to being a simple ordinary differential equation, there is something that you should notice. What is in here is nothing but the Hamiltonian operator. So, this actually is saying that H, let it operate upon psi of x. What is it that you have on the right hand side? You are getting psi back, right. You are getting the same function, but multiplied by the constant E. So, that is what is happening. You are getting psi back, or I can say, I mean, the effect of H operating upon psi is equivalent to multiplying psi by the constant E. That is what this equation says. So, what is it? It means that psi has to be an eigen function of the Hamiltonian operator. That is the meaning of this equation, right. So, therefore, if you find an eigen function of psi, sorry, so if you find an eigen function of H, then you have determined a possible psi. As I was telling you in the morning, any given operator can have an infinite number of different eigen functions, and each would have its own associated eigen value, right. So, therefore, let me say that I have several different eigen functions of H. So, what will I do? I will write them as psi 1 of x, psi 2 of x, etc. I may have several different eigen functions. In principle, normally you have infinite number of them, and each one will have its own associated eigen value, right. The eigen values will usually be different. So, let us say psi 1 has the eigen value E1, psi 2 has the eigen value E2, etc. if you say psi n of x, then it has the eigenvalue E n. And what is going to happen? Imagine I allowed S to operate upon psi n of x. What will be the answer? I shall get E n multiplied by psi n of x, correct. So, this function psi n of x is a potential choice for me as far as my product is concerned. Where is my product? This is my product. See, what is our ultimate aim? Ultimately, I want to determine capital psi, because the basic equation that we have is the time dependent Schrodinger equation, which is there on the screen, right. It is there on the screen. I have also written it here. So, this is the equation that we want to solve, but then we are looking for special solutions of the form capital psi is equal to small psi into capital T, and capital T we have already determined. The functional form is written here. Now, what about small psi? The answer is that small psi has to be, the only condition is that small psi has to be an eigenfunction of H. If there are several possible eigenfunctions, then each one of them is going to give me a solution of the original time dependent Schrodinger equation. So, therefore, if I now took psi n of x, I take psi n of x, I will have to multiply it by capital T of t. What will be the expression for capital T of t? The answer is, it is going to be the constant a, right, e to the power of minus I. Well, I will have to put in the value of e, but for the nth eigenfunction, the value of e is going to be E n. The value of e is going to be E n. So, E n t by h cross would be my solution. So, this will give me a solution of the time dependent Schrodinger equation, right. But in order to find the solution, you see, it is really not necessary for me now to worry about this equation. It is enough if I can solve this equation, right. If I can solve this equation and find all the possible eigenfunctions and eigenvalues of the Hamiltonian, then what I can do is I can take any one of them, for example, psi n multiplied by a constant and then e to the power of minus I E n t by h cross. I would have a solution of the original time dependent Schrodinger equation. That is how it is. So, therefore, you see, we starting from here, we have derived a simpler equation which small psi has to obey, and this equation is known as the time independent Schrodinger equation. And look at what has happened. I have derived the time independent Schrodinger equation starting from time dependent one. So, therefore, the time dependent one is more basic, and the time independent one can be obtained only if your potential energy has no dependence on time. So, only in such cases will you be able to derive this equation. But once you have derived this equation, you see, I do not really have to worry about this equation, because I can get solutions of this equation simply by solving this equation and then taking the solution and multiplying it by a constant and e to the power of minus I E n t by h cross. Now, yesterday I was telling you that the wave function, okay, eventually I will have to normalize the wave function. If it does not satisfy the normalization condition, I shall have to normalize it. So, any constant that is occurring here, you see, it is irrelevant, because eventually what I will do is I will normalize my function. So, therefore, what I will do is this a, I am going to absorb it into my psi n, because after all eventually you will have to multiply psi by a suitable constant, which will be done. So, this constant we can just say, okay, it is absorbed as a part of this psi n, okay, and therefore, from now on we will write the solutions as psi n into e to the power of minus I E n t by h cross. Now, let us, having found the solution, let us look at the properties of the solution. So, this is what we have found. Let us imagine that I am thinking of the probability density. What is the definition of probability density? Well, if you remember, we had defined it as psi of x t star multiplied it by psi of x t. And what is the use of this? Well, if you are interested in an interval dx starting from x to x plus dx, then the probability of finding the particle in that small interval will be equal to psi star psi dx, correct. This is a part of our postulate, the first postulate actually. So, what is happening is that I have the particle moving in one dimension, then this is a small length dx lying between the point x and the point at x plus dx. The probability that your system will be found in this small interval is given by that expression. And you know that psi is a function of time. So, therefore, naturally you would expect that psi star psi will also be a function of time, and therefore, the probability of finding the system in this interval we would expect will change with time. That is the general situation. In general, the most general situation will be that the probability of the finding the system in this small interval will go on changing as time passes, because the state function we expect is changing. But let us imagine that the state function is given by this particular expression. What will happen if you had this particular expression? Let us look at it by substituting this expression in here. So, psi of x is going to be psi n of x e to the power of minus I e n t divided by h cross, correct. This is I of x, then you have to multiply it by dx, and you have to multiply it by the complex conjugate of this, which will be equal to psi n of x e to the power of minus I n t by h cross with a star written. And what does this star mean? It means take the complex conjugate, and I hope you remember how to take complex conjugates. The way to do that is, you see, you look at the expression, wherever square root of minus 1, that is I, occurs, you have to replace I with minus I. So, if you look at this expression, well, there is a minus I sitting obviously here, you have to replace it with minus I, that means this is going to become a plus. I can remove the star, but then I do not have the full detailed expression for psi n, maybe it will contain an I, in which case I will have to replace that I with minus I. So, the result is actually nothing but the complex conjugate of psi n, right. This is what happens, and then you look at this expression and you look at this term and that term together, right. One has e to the power of plus, the other has e to the power of minus, and you would see that the two things combine and give you the answer unity. So, therefore, what is the net result? The net result is that I get an answer which is psi n star of x psi n of x dx. So, even though originally you see time was there in our expressions, it was there originally in this expression, time is there, but if it so happens that the state function is given by such an expression, then what has happened, the answer that you get is independent of time. So, the probability that your system or your particle may be in a small interval of length dx, it does not change, even though your state function, you look at the state function actually depends on time. There is time dependence here, but this dependence is very special. It is very special in the sense that if you actually calculate the probability density is this product, or if you calculate the probability which includes that dx also, then you find that it is independent of time. So, if the system is sitting in this state, the probability that the system may be found in a small interval of length dx does not change with time, even though the system itself is evolving in time, probability does not change, and this is the reason why such a state is referred to as a stationary state, because the state is stationary as far as time evolution is concerned, the probability does not change. So, such a state is referred to as a stationary state. Now, in addition to this, suppose I have any operator A, you think of any operator A, for example, you can think of different operators, maybe the Hamiltonian operator, or maybe the momentum operator corresponding to momentum, or maybe the operator for position. These are the simple things that you can think of. You think of any operator, and I want to think of the expectation value of A, which is something that we have defined today. The expectation value is defined as integral of right. I am writing the expression that is appropriate for a one dimensional system. So, integral of psi star A psi dx divided by integral of psi star psi this is what it is. Now, just the way we have done in this case, you see, I can proceed to evaluate this also. Well, as far as the denominator is concerned, it is obvious psi star psi, these are capital psis, but then if you substitute it, which expression, where is the expression? This expression in here, this product is going to be independent of time, this product is going to be independent of time. So, the integral of it over the entire space will be independent of time. Okay, I need space. So, this is equal to, you can see the denominator, it is nothing but integral of psi star nx psi nx dx over the entire space is simple, even though I have not put the limits, it is over the entire space. Actually, if you want to put the limits, they are from minus infinity to plus infinity. Maybe I will do it so that there is no confusion. And then you look at the numerator, what has happened, you have the operator A and you have operator A operating upon psi n of x e to the power of minus I e n t divided by h cross, and this is going to be multiplied by the complex conjugate of that. So, I am going to get psi n of x e to the power of minus I e n t by h cross. There is a star here, and then I will have dx, and I would have to integrate from minus infinity to plus infinity. So, this is what happens, And now imagine, you see, you think of an operator like the Hamiltonian operator or the momentum operator, these are things that normally do not depend upon time, right. I have assumed that for this problem the Hamiltonian is independent of time. So, Hamiltonian does not depend on time, momentum operator is a simple operator, there is no time dependence, position again is independent of, operator is independent of time. So, if you are thinking of a situation where this A does not depend upon time, definitely this A will not affect this term, it will not affect that term. So, you can move this term to the left side of A, and on the left side of A what is it that you have? You have this complex conjugate. So, this star can be taken inside, this minus sign will become a plus. So, once you move this outside, this and that are going to cancel and you are going to get 1. So, I can safely remove this term as well as that term, and you look at the result. You find that the result has no time anywhere, it is independent of time. So, therefore, for a stationary state the expectation value of any operator is independent of time. And remember, we talked about the importance of expectation values, right. The importance is that if you think of making a measurement, and if you took the average of all the answers that you get, that average is just equal to this expectation value, right. So, if the system is in a stationary state, what happens? All the properties that you expect, or all the properties that you measure and find out, they are all independent of time, whether you measure the system now or maybe tomorrow or maybe 1 year later. If it was in the stationary state, you are going to get the same answer, okay. So, that is what this means, and that is again the reason why this kind of states are referred to as stationary states, okay. But then, is that the most general solution of this equation? See, after all, what is it that we wanted? We wanted to solve this equation, but what we have found is actually certain special solutions, right, for which the time dependence and the position dependence can be separated out, right. So, that is, those are the solutions that we have found, but can I have more complex solutions? The answer is yes. For example, okay, let me say that I have one stationary state which I shall denote as psi 0, okay. It has an energy E 0. So, therefore, the total time dependent wave function for this will be psi 0 into e to the power of minus I E 0 t by h cross, right. So, let me imagine, what I am saying is I have the state psi 0 having an eigenvalue E 0, and then I know that psi 0 into e to the power of minus I E 0 t by h cross actually obeys this equation, correct. And similarly, if I have another eigenfunction which I shall denote as psi 1, this time having a different energy, right, then what will happen is that I will have e to the power of minus I E 1 t by h cross. Now, I refer to this as the energy of the system. Why did I do that? The answer is actually extremely simple. If you look at the time independent Schrodinger equation, which I seem to have removed, if you look at the time independent Schrodinger equation, it said that h psi n is equal to E n psi n. This is what it said. This means that E n is an eigenvalue of the Hamiltonian operator, and remember, Hamiltonian operator is the operator associated with energy, and therefore, if you make a measurement of energy according to one of our postulates, if you make a measurement of energy, what would be the answer? It will be an eigenvalue of the corresponding operator. So, therefore, these are actually nothing but answers that you are going to get if you make a measurement of energy of the system, and that is the reason why I will refer to En as the energies of the system, because if you make a measurement, this is going to be the answer. Measurement of the energy, this is going to be the answer. So, now suppose I have one eigenfunction which I shall call psi 0 having the eigenvalue E 0 and another one having the eigenvalue, sorry, having another eigenfunction which is I 1 having the eigenvalue E 1. Now, it is actually possible for me to multiply the first by some constant C 0, the second by some other constant C 1 and add the two together. You take the first solution, multiply it by any constant you like, take the second solution, multiply it by some other constant, add the two together. It is very easy to prove that this also satisfies the original time dependent Schrodinger equation, right. This is a property of the time dependent Schrodinger equation. If you have two solutions, you can just add them together and the sum will also be a solution of the same equation, right. So, having found special solutions, these are actually special solutions. I 0 into e to the power of minus I E 0 t by h cross is a special solution. This one also is a special solution. Why are they special? Because they are products of two functions which are multiplied together. The one is dependent only upon x and the other is dependent only on t. So, having found such solutions, it is possible for you to add them linearly. You can add the two of them linearly and get a new solution, right. It is not difficult to show that the sum actually satisfies the original equation, very easy. It is only a question of taking this equation and substituting it there, and you will see that this is the solution, right. The equation is automatically satisfied by this sum. Okay. And further, you see, if you think of such a state, you can actually calculate, maybe I shall leave this as an exercise. You can actually calculate psi star psi, the probability density, and you can find that for such a solution psi star psi is dependent upon time. It will change as time passes, so that it is not a stationary state. Okay. Such a state does not represent a stationary state. It represents a state in which the probability density will change with time. Okay. Okay, if you have questions, of course, I shall be happy to answer them. Now, we have all the machinery that we need to look at chemical examples, and that is what I am going to do. I am going to look at the simplest possible example. So, the simplest possible example is this. I imagine that I have a particle which is moving in one dimension. Okay. And I shall further put the condition that it can move only in a certain length of that line. So, here is x is equal to 0 and there is x is equal to L, and I will say that the particle is allowed to move only in that range. Why? Because beyond this point or beyond that point, I will say that the particle will experience a potential that is infinitely large. So, here I will say the potential is infinitely large in this region. I will also say that in this region the potential is infinitely large. So, if you are thinking, I will tell you the physical motivation for doing this in a few seconds, but suppose I am going to represent the potential energy along the vertical axis, right. I am going to represent potential energy along the vertical axis, and this is my horizontal axis, which is actually x. Then what will happen is that I am going to assume that the potential energy is 0 if the particle is in this region within the box. That means, if x is between 0 and the length of the box, right, if x is between 0 and L, V of x is assumed to be 0. Well, if the particle is outside the box, what will happen? The potential energy will jump to a very large value. So, suddenly when I go from inside the box to the outside, the potential energy jumps very rapidly to a very high value, which actually will be taken to be infinity. This height, of course, I cannot represent infinity on the blackboard, but that is how the potential changes, and similarly on the other side also. The potential energy jumps to infinity as you go out of the box. Now, before I go on to describe this model, I want to tell you why think of such a model, which obviously is not physically realizable, but it is a very useful model. I mean, you all know of for a conjugated systems, right. You have a conjugated molecule like CH2, CH, CH, CH2, or if I stop there, I will think of a more longer system. This is hexatriene, right. It has 6 carbon atoms and 3 double bonds. Now, I suppose you would know that this is a pi system, each well, I do have to assume some knowledge of orbitals and hybridization and so on. You would know if you ask any organic chemist, he will tell you that each of these carbons are sp2 hybridized, that will leave a p orbital perpendicular to the plane of the molecule. So, therefore, I can represent them. I would have p orbitals in this fashion sticking out on each one of the carbons, and the p orbitals actually overlap and leads to what is referred to as the delocalized system in the conjugated molecule. And each carbon actually contributes 1 electron to this delocalized system, which is referred to as the pi system of the molecule. So, in this case what happens is that because there are 6 carbons, each carbon contributes 1 electron. So, we say that the pi system contains 6 electrons. So, if you think of any one of the pi electrons, let us say the electron is sitting here, but you see this orbital and that orbital overlap, and therefore, what happens is that the electron can move from here to there to there to there to there, etc. That is the meaning of saying that the system is delocalized. The electron can actually move from one end of the molecule to the other end. So, you think of any one of these 6 electrons, they are free to move from here to the other end, and suppose one electron is moving in this direction. What is the potential energy that the electron will feel? That means rho is a very schematic appearance of the potential energy that the electron will feel if it is moving along the molecule. See, if it is moving along the molecule, right, let us say it starts somewhere here, or maybe it starts somewhere here at this end. There it is not very close to the nucleus, it is not very close to the carbon. So, therefore, the potential energy will be relatively high, while if it is moving in this direction somewhere here, it is going to be somewhat close to the nucleus, and therefore, what will happen? The potential energy will start decreasing. So, if you plotted the potential energy as a function of the position of the electron, what is going to happen is that the potential energy will start decreasing. It at the nucleus itself, it will reach a very large but negative value, right, the potential energy, and then as it moves further, what will happen, the potential energy will actually increase, right. This is the position of the nucleus, but as the electron is moving away from the nucleus, the potential energy will increase, reach a maximum and then decrease to a very large negative value when it is near the second nucleus. And as it moves further, what will happen, the same kind of thing will go on repeating again and again and again. Well, maybe I will draw it better in here. This is how the potential energy will change. So, how many such? You will have 6 of them, right? No, 5 bonds, okay. Right, 1, 2, 3, 4, 5. Oh, I think I have drawn one too many. So, here is carbon atom 1, that is carbon atom 2, carbon atom 3, 4, 5, 6, and then what will happen to the potential energy? It actually will increase. Okay. So, this is how the potential energy will be changing as the electron moves along the molecule. So, if we wanted to construct a model for the motion of this electron, actually what I should do is I should think of having a potential energy which has this kind of variance with the distance, and then try to analyze that, but this is obviously very difficult. It's such a potential, solving the Schrodinger equation for such a potential is extremely difficult. So, therefore, what people have done is they said, okay, let us not worry about the fact that there are variations inside the molecule. What is important is that if the electron is within the molecule, its potential energy is low because it feels the presence of the nuclei. Well, if we take the electron outside the molecule, it does not feel the presence of the nuclei, and therefore, its potential energy has to be high or large, right. So, therefore, what is the simplest thing that you can do? You can say, okay, the simplest thing is that imagine I have a certain length, within that length the potential energy is the same everywhere, that is only an assumption, and outside the potential energy is large, right. It is actually large, it is not infinitely large, but as an idealization we say, okay, outside it is infinitely large, because that makes things extremely simple. In fact, later on I will tell you what happens if you did not assume this. If you can assume that the potential energy outside is not infinitely large, and then what will happen, that I will tell you maybe tomorrow. But let us look at this model. What is the model? I have already given you this. See, here you are saying now that the potential energy is the same everywhere. So, the potential energy, this curve, these curves are replaced by a flat potential energy, but then outside, of course, you see what I should have done is I should have had a potential which has this kind of appearance. That is what I should have actually done, because outside the potential energy is not infinitely large, but to make the things simple, I shall just say that this height is infinitely large, and that is what has been done in the description that I have already given you. Okay. So, let me now go ahead and define things quantitatively. So, precisely speaking, what I have is V of x, I am going to say it is equal to 0 if x is between 0 and capital L, where L is the length of the box, and particularly if we have a molecule like this etc. in, what would be the typical length of the of the molecule. Well, you know that a carbon carbon double bond roughly is of the order of 1.4 or 1.5 angstroms. So, if you have 5 such bonds, roughly the bonds will need a length of how much? 5 bonds, 5 into 1.5. So, roughly 7 angstroms, 7.5 angstroms is the size of the box. So, I am telling you this so that you have an idea as to how big the box is. So, what am I thinking of? Essentially, I am thinking of an electron which is confined to a one dimensional box. It is assumed to move only in one direction, and that box has a size of maybe about 7 or 7.5 angstroms. Or if you had a longer molecule, let us say you have a conjugated system of 12 carbon atoms, then it will be twice as long. So, it may be about 15 angstroms long. So, this L is of the order of a few angstroms, let us say. That is the system that I am interested in. So, if V of x, if x is between 0 and L, V of x is equal to 0, while if x is outside, V of x is actually infinitely large. That is the nature of the potential. And what is it that I want to do? I want to look at my time dependent Schrodinger equation. What is the equation? It is going to be I h cross dou psi by dou t is equal to h psi. This is my time dependent Schrodinger equation. Now, this obviously is an example where the potential energy does not depend on time, it does not change with time. So, therefore, it is possible for me to find what are referred to as stationary states, right. And in order to find stationary state, what should I do? Answer is very simple. I just have to solve, I do not need to solve this equation, but it is enough if I can solve the equation H operating upon psi is equal to E psi. That is enough. If you can solve that equation, then you can be happy, because once you have solved this equation, you can take that psi and multiply that psi by e to the power of minus I E t by h cross. You will get a solution of the first equation. So, now I have to solve this equation, and what is this equation? Let me write this in a little bit detail. What this equation says is minus h cross square by 2m dou square upon dou x square, because that is our operator for kinetic energy. Hamiltonian contains kinetic and potential energies. So, minus h cross square by 2m dou square upon dou x square plus V of x is my Hamiltonian operator. So, this is the equation that I should solve. This is the eigenvalue equation that I should solve. Well, I think I will stop here and continue in the next lecture. Thank you for listening.